So in this video, we're going to go through this in-class worksheet on chemical bonding and molecular geometry. We'll go through each of the problems. So our first problem, we're asked to draw Lewis structures of 3 molecules. And so we can start off with this one, NH2Cl. And remember, whenever we draw a Lewis structure, the first thing we should do is count valence electrons. So nitrogen is going to have 5 valence electrons. Each hydrogen is going to have 1 for 2 valence electrons. And then chlorine is going to have 7, giving us a total of 14 electrons. And so when I go ahead and draw this molecule, I'm going to start and put nitrogen in the middle. All right, the least electronegative non-hydrogen atom is your central atom. I'm then going to connect everything with single bonds. So we have hydrogen, hydrogen, and chlorine. Now what we're going to do is we're going to add electrons to the outer atoms first, right? So we've added so far 2, 4, 6 electrons. We have to get to 14. So I'm going to add pairs of electrons around the chlorine. So we had 6, 8, 10, 12. So that gives us 12 total electrons. And so we need to add 2 more electrons. And when we look at nitrogen here, we see that nitrogen only has 6 electrons around it. So we can put 2 more electrons on nitrogen. And this would be our Lewis structure for our first molecule. In our second example, we have HCOOH. So again, we're going to count electrons. We have 1 from the hydrogen, 4 from the carbon, 6, 6, and 1. So we have 10, 16, 17, 18 electrons. And in this case, we're given a little note. And anytime you see the COO, what that really means is COO. And then this left-hand hydrogen is bonded to carbon. And then this other terminal hydrogen is bonded to oxygen. So at this point, I've added 2, 4, 6, 8 electrons. So what I'm going to do is add lone pairs to my outer atoms, which we're going to start with the hydrogens. So we have 2, 4, 6, 8. We need to get 18. So 10, 12, 14, 16, 18. And at this point, we've added all 18 electrons to our structure. But we want to ask ourselves now, do all second period atoms, like carbon, do they have an octet of electrons? Do they have 8 electrons around it? And we see in this case, this carbon only has 6 electrons. So we need this to be an octet. So what I'm going to do is I'm going to take a pair of these electrons here, and I'm going to turn these into a double bond. So I'm going to erase one pair of electrons, come down here and form our double bond. And now we have our structure, which everything hits an octet, and all of the electrons are accounted for. In our last case, we have CS2, so 4 electrons from carbon. Each sulfur has 6, so that's 12 for a total of 16 electrons. Carbon will be our central atom, so sulfur, sulfur, and then add lone pairs to the outer element. We have 4 electrons accounted for, 6, 8, 10, 12, 14, 16. Now all of our electrons accounted for, but again, notice carbon does not have an octet. So what I'm going to do is I'm going to take lone pairs of electrons, turn this into a double bond, lone pair of electrons, turn this into a double bond. And so what we're going to end up with, I'll redraw it now. Carbon with 2 double bonds, and sulfur with 2 lone pairs on it. So there's our structure. In our next question, we're asked to draw the structure of NO2 with a minus charge. And so again, if we count electrons, we have 5 from the nitrogen, we have 12 from the 2 oxygens, and then from that -1, an extra electron from that -1 charge. So that's going to give us a total of 18 electrons. So I'm going to start off with my nitrogen. What I'll do now is add those 2 oxygens. So I'm just going to start off like this. Now we need to add our electrons. We have 4 electrons accounted for. We need to get to 18. So we'll start by putting them on the outer atoms. So 4, 6, 8, 10, 12, 14, 16, 18. So now all electrons are accounted for. But one of the things to note, again, we don't have an octet on our nitrogen. There's only 6 electrons. And so what we're going to have to do is form a double bond. And one of the things to notice is we could take a double bond from this oxygen and push these electrons to make a double bond. Or we could push electrons from the right oxygen to form a double bond. Now notice the fact that I can do this from 2 different oxygens that are equivalent is a big hint that we're going to have resonance structures. So what I'm going to do is I'm going to redraw this with a double bond, and I'm going to start off with that double bond from my left oxygen. And then knowing that we could do it from either means we're actually going to have 2 different resonance structures. So remember, when we have resonance structures, we're going to put them in brackets. And I'm going to draw the other resonance structure, which has the double bond to the right oxygen and a single bond to the left oxygen. And each of those would have a -1 charge. I'll put the negative charge out here. And the Lewis structure of NO2 minus is actually both of these resonance structures. And again, what this resonance structure means is it's not that we have a double bond and a single bond. It's really that the double bond and the single bond are really both, right? So they're really 1.5 bonds. We need 2 structures to represent the reality of that molecule. In our next question, we are asked to calculate some electronegativity values and identify them as being polar or nonpolar. And so we have carbon Se. So again, look at carbon 2.5, and then Se 2.4. And so we have 2.5 for carbon minus 2.4 equals 0.1. So this would be a non-polar bond. For our ClBr, here we're looking at Cl is 3 minus 2.8. This is 0.2, so non-polar. Now we have nitrogen, hydrogen. So nitrogen is 3 minus 2.1, 0.9. So this is polar. And if we were to draw the dipole arrow, it's polar towards the nitrogen. Carbon hydrogen ends up being 2.5 minus 2.1, 0.4. This is a non-polar bond. KBr, 2.8 minus 0.8, 2.8 minus 0.8 equals 2. So this is ionic, which is hopefully what we would have predicted from something on the metal and a non-metal. And then we have our titanium, 1.5. Chlorine is 3. So we have 3 minus 1.5 equals 1.5. And so this is going to actually be a polar covalent bond. And so now in our last problem, we have 3 more Lewis structures, and in this case we are asked to draw the Lewis structure, determine the electron group, molecular geometry, and determine if the molecules are polar. So first, it's Lewis structure time. So we're going to go through, and we have 2 electrons from hydrogen, 4 from carbon, 6 from oxygen for 12 electrons. Carbon's our central atom. So we're going to have hydrogen, hydrogen, oxygen. We've added 6 electrons. We need 6 more. And so you can practice this on your own, but when you end up with it, you're going to end up with a double bond to that central carbon. So we get our structure looks like this. So our electron group geometry, we have 3 things coming out, a single bond, 2 single bonds, and a double bond. So we have trigonal planar. And the molecular geometry is going to be the same since we have no lone pairs. In terms of polarity, the oxygen-carbon bond is polar. The carbon-hydrogen bonds are nonpolar. And so overall, we are going to be polar, and it's going to be polar in this direction. So we can call this a polar molecule. In our second example, we have BCl3, so 3 electrons from boron, 21 from the 3 chlorines, which is 24 electrons. We have boron in the middle. We have 3 things coming out. Now we have 6 electrons. We need 18 more. Now we have all 24 electrons accounted for. And when we look at this, we can say this is also going to be trigonal planar for both the electron group and the molecular, right? 3 things coming out of that central point. And while each of these bonds are indeed nonpolar, they all point in opposite directions. And so this is a nonpolar molecule. So there are polar bonds, but the molecule will be nonpolar because each of those bond dipoles will cancel out. Our final example is SeCl2. And so Se has 6 electrons. Chlorine has 7 each for 2 of them. So that's 14. That's going to be 20 electrons. Se is in the middle. So we'll start by connecting it with 2 chlorines, adding electrons to each of those 2 chlorines first. At this point, we have 16 electrons, so we need to add 2 more to the Se. And so this is our correct Lewis structure. And we might want to redraw this now because as we look at this, here we're going to see our electron group geometry is 4 things coming out. So this is a tetrahedral. And so it might be helpful once you recognize that to be tetrahedral, I'll move this over a little bit, to redraw this to show that. And I'm going to draw it with the electrons this way and our chlorines coming down like this. Right, so we can draw both chlorines and that selenium all in the plane of the paper. So the molecular geometry is bent. And in terms of polarity, chlorine is more polar than the selenium. So both of those chlorines are pulling away. So we can call it polar. And if we wanted to draw a bond dipole, it's actually going to be straight down towards the chlorines. And so I hope that's helped go over some of the chapter 4 material. Thank you.